Welcome back to my rubber heart. Today we are going to explore one of the most important but often underestimated components in any rubber compound, the fillers. Now, when people outside the industry hear the word filler, they usually think of it as something cheap, something that dilutes or bulks up a formula. But in rubber, fillers are so much more than that. They can be the difference between a high-performance compound that excels in durability, tear resistance, and thermal behavior, and one that simply doesn't perform. The beauty of fillers lie in how they modify the behavior of rubber from the inside out by interacting with the polymer chains, the vulcanization system, and even other additives. Let's begin with reinforcing fillers, because these are the ones that most people in the industry associate with serious performance. Carbon black is the classic example here. It's more than just a black pigment. It plays a structural role in the rubber matrix. Its tiny particle size and high surface area create an enormous amount of interfacial contact with rubber chains. This interaction restricts polymer mobility near the filler surface, increasing modulus, tensile strength, and abrasion resistance. The result is a tougher, more resilient rubber. You'll find carbon black in applications like tire treads, conveyor belts, seals, and gaskets, anywhere that high mechanical strength and dynamic performance are needed. And the type of carbon black matters too. Finer particles with higher structure give more reinforcement, while coarser grades can be used to control heat buildup or improve dispersion. Closely related in function but very different in chemistry is precipitated silica. Silica doesn't naturally bond well with nonpolar rubbers, but when it's paired with a silane coupling agent like TES-PT, it becomes a powerful reinforcing filler. The silane acts as a chemical bridge between the silica surface and the rubber chains, allowing stress to transfer more efficiently across the matrix. This is critical in modern tire technology. Silica silane systems allow for the production of tires with lower rolling resistance and better wet traction without compromising wear. That's why they've become essential in the formulation of so-called green tires. You'll also see silica in footwear soles, industrial rollers, and even medical elastomers when color purity or non-black appearance is required. Then there are the non-reinforcing fillers, often called extenders. These don't contribute much to mechanical strength, but they serve essential roles in processing and economics. Calcium carbonate is probably the most widely used among them. It's cheap, it disperses relatively easily, and it allows compounders to reduce the cost per kilo of the finished rubber. While it doesn't bond with the rubber on a molecular level, it does influence compound viscosity and flow. In less demanding applications like rubber flooring, hoses, or matting, it's often used in fairly high loadings. Talc is another interesting non-reinforcing filler. Because of its platy morphology, talc acts as a processing aid. It helps with flow, reduces die swell during extrusion, and improves surface finish in molded parts. It doesn't reinforce the rubber, but it can enhance dimensional stability. Kaolin clay plays a similar role. While its impact on tensile properties is minimal, it can improve barrier performance, and with surface treatment, its compatibility with different rubbers can be enhanced. Moving beyond the basics, we get into the world of functional fillers. These are fillers that bring specific properties to the compound, properties that aren't just about strength or cost, but about how the rubber performs in a particular environment. One of the best examples here is aluminum trihydrate, or ATH. This is a flame retardant filler that works by decomposing endothermically, meaning it absorbs heat and releases water when heated. That water helps to cool the material and dilute flammable gases, slowing down combustion. ATH is widely used in cable sheathing, insulation, and roofing membranes where fire safety is critical. Its cousin, magnesium hydroxide, operates on a similar principle but decomposes at a slightly higher temperature, making it more suitable for thermoplastics and heat-resistant elastomers. Another fascinating group of functional fillers is the conductive types. When you add certain grades of carbon black, graphite, or even carbon nanotubes, you're not just reinforcing the rubber. You're creating a conductive network within the matrix. These particles form continuous paths that allow electrons to flow, making the rubber electrically conductive or even EMI shielding. This is crucial in anti-static flooring, fuel hose linings, and rubber components used in electronics where electrostatic discharge needs to be controlled. Mica is often used when you need barrier properties. Its platelet shape helps block the passage of gases and moisture, which is useful in things like automotive weather seals or gaskets for chemical-resistant linings. Hollow glass microspheres, meanwhile, reduce the overall density of the compound. They can help create lightweight parts without sacrificing volumes. These are used in things like flotation devices, specialty footwear, and even vibration damping components. And then we have nanofillers. These are on the cutting edge of filler technology. Materials like nanoclay, nano-silica, and carbon nanotubes provide reinforcement at incredibly low loadings because of their massive surface area and high aspect ratios. They change the game in terms of barrier properties, electrical performance, and even fatigue resistance. But they require extremely precise dispersion to be effective. Their cost is higher, but in critical applications like aerospace seals or medical devices, they are proving their worth. What makes all of this so powerful is that the filler isn't just a passive ingredient. It interacts with the rubber matrix in profound ways. It affects how the rubber flows, how it cures, how it resists wear, conducts electricity, or withstands heat and fire. Whether you are using a high-structure carbon black to create a tire that can hug the road, or tens of thousands of kilometers, or a dose of ATH to stop a cable from catching fire in an emergency, you're shaping the material on a molecular level. And most of the time, you're not just using one filler, you're combining them. Maybe some silica for reinforcement, a touch of talc to help it flow, and a bit of clay for cost efficiency. That's the real craft of rubber compounding, knowing not just what each ingredient does in isolation, but how they play together in the final material. Thanks for joining me today on My Rubber Heart. If this gave you a new appreciation for what really is going on inside your rubber compound, make sure to subscribe and drop a comment. Whether you are working on a high-performance tire or a simple gasket, your choice of filler might just be what makes the difference. See you next time. Until then, stay elastic and stay curious.